Good afternoon, everyone. This is our class today about whiplash injury and understanding the importance and relationship between vehicle crush and patient injury. This is a very important topic in the PI world. And let's start out talking about a recent story in the San Francisco Chronicle. Oh, okay, got that. Okay. On Saturday, November 22nd, 2014, the front page of the San Francisco Chronicle led with this headline: 11-story plummet, what onlookers saw. The first inkling that office workers scurrying along Montgomery Street had that something was wrong came when they looked up to see a blue blur falling from the sky. Some thought it was debris, but then it got closer, and the crowd began to scream and scatter. It was a man plummeting 11 stories towards them. With a thump and a crash of shattering glass, the middle-aged window washer smashed into a moving car just after 10 a.m. Friday morning. He lay wincing and miraculously alive on the crumpled green roof of a Toyota Camry. Peter Melton from the California Department of Industrial Relations noted, "It seems pretty clear that the cushioning of the car he fell onto kept him alive." So, the universe and our world are under the control of principles of math, physics, chemistry, etc. The principle of inertia have likewise been with us, but they were not always officially acknowledged through publication until Isaac Newton wrote in the year 1687 the book Mathematical Principles of Natural Philosophy. Inertia is the resistance of a physical object to any change in its state of motion or rest. As stated, an object in motion will remain in motion unless outside forces act upon that object. Likewise, an object at rest will remain at rest unless an outside force acts upon that object. When the laws of inertia are applied to a whiplash injury, it's quickly pointed out that different parts of a single object can have different inertias, depending on how the object's mass is distributed. Specifically, the human body, a single object, can have different inertias between the trunk and the head. In a rear-end motor vehicle collision, the struck vehicle, its seat, and trunk of the occupant are quickly propelled forward, while the head, having its own inertial mass, will remain at rest. The head remains still while the body is moved forward under the head. This is the appearance of the head extending upon the trunk, the so-called hyperextension phase of a rear-end motor vehicle collision. And here we get a good picture of that. Under these circumstances, the most vulnerable part to injury is not the trunk nor the head, but rather the part of the body that balances these two larger masses to each other, the neck. Because of the large inertial masses of the trunk and the head, the neck is historically very vulnerable to inertial injury. In this context, an inertial injury means that there is no direct blow or contact injury to the neck. Published experts in motor vehicle collisions have completed experiments or made observations which conclude that the degree of patient-passenger injury from automobile collisions is not related to the size, speed, or magnitude of damage of the involved vehicles. Now, inertial injuries are not related to vehicle damage. And instead, they're related to the acceleration of the struck vehicle. That's the key term, acceleration. Factors that reduce acceleration and the likelihood of inertial injury include dry roads, the driver's foot being on the brake, crushing of the involved vehicles, and driving a larger vehicle that is hit by a smaller vehicle. On the other hand, things that increase vehicle acceleration will increase the likelihood of inertial injury. So these are wet or icy roads. The struck vehicle was moving slowly forward already. The vehicles not crushing. That's a key point. Vehicles involve not crushing, and driving a smaller vehicle is hit by a bigger vehicle. Now, the science says the kinetic energy of the striking vehicle must equal the kinetic injury of the struck vehicle plus vehicle crushing. So to simplify that, the kinetic energy prior to the crash, by the striking vehicle, should equal the kinetic energy of the vehicle plus vehicle crush. So if you look at the relationship here, we have a high vehicle energy crash, high acceleration, high inertial injury, but low vehicle crushing damage. So you see the kinetic energy of the vehicle is very high. The struck vehicle is very high. Now, in another example, we have low struck vehicle energy, low acceleration, but inertial injury, low inertial injury, but high vehicle crushing. So the energy goes over to the car side versus the passenger side. So this is a super important concept in that cars are being made stiffer and stiffer and stiffer. All right, this is a research project from the Spinal Research Institute of San Diego. They have a ton of great material. I recommend you check out their website. And this shows an experiment they did where they did a couple of crash tests, and they measured the damage to the car. So if we look, how about we go on the bottom left-hand side? Let's look at Chrysler LeBaron here. They show the back of the car after several crashes here, as high as 8.6 miles an hour. All right, we look at the, what do we got here? We have a little Honda over here. All right, we have 3 crashes, 3.7, 6.6, and 7.2 mile per hour impacts, no damage. All right, we have a Mercury, it looks like, a sedan. And then we have a 10 mile, 9.9 crash and no damage to the vehicle. So what's happening is that cars are being made stiffer and stiffer to decrease the amount of it's going to cost to repair them. I'll repeat that. Cars are being made stiffer, not only the exterior of the car, but the interior of the car, so they don't get damaged. Those of us who've been around for a while, you know that very common thing in a rear impact in the past was that the driver in a good rear impact would end up in the back seat because the seat back would break and they'd end up in the back seat. So that, again, is a type of crushing, and it dissipated the energy. But now the seats are much, much stronger, and that rarely happens. I mean, you barely haven't heard that in years and years and years and years. All right. Now, so the bottom line is this. In racing cars, they sacrifice the car to save the driver. In passenger cars, they sacrifice the people to save the car. Right? And this is why there's such a epidemic of people running around with bad necks from these car accidents. I was just thinking the other day, I've been in 7. I've been rear-ended 5 times and then broadsided once, broadsided twice, actually. You know, my neck is not in great shape because of that. And, you know, because again, I was sacrificed to save the car. Now, the first one, the worst one, probably the highest speed one, the car totally smushed. So that one probably saved me a bit, but the other one's not so much. So what does this mean for your cases? Published experts in motor vehicle collisions have shown that the degree of passenger injury is not related to the size, speed, or magnitude of damage to the involved vehicles. Navin and Romley, 1989, stated that experimental results indicated that some vehicles can withstand a reasonable high-speed impact without significant structural damage. A review of accidents indicates that a significant percentage of accidents occur with little or no accompanying vehicle damage. As the vehicle becomes stiffer, the vehicle damage costs are reduced. However, the occupant experiences a more violent ride, which increases the chances for injury. The average acceleration experienced by the occupant in the elastic/no damage vehicle would be approximately twice that of the plastic or damaged vehicle. All right, so I think that gives you a good introduction to the concepts here. And next time we will go over a ton of research that back up this concept. So have a great week. Hope you enjoy the video and talk to you soon.